Cool. Hello, everyone. Welcome to the final talk of this year's Astronomy Day and Night from Uppsala University. I'm here at Biotopia. I'm an astronomer. My name is Adam Rains. I'm at Uppsala University. And so for everyone who's in Uppsala, across the road, we have our observatory, which will be running for probably up until 4, so there's a bit of time after this talk to catch it if you're still around. But until then, if you're listening to me, you're going to hear about some planets. So today we've heard some talks, a mixture of talks in Swedish and in English about Lynn gave a talk earlier in the day about how stars are born and how stars live and end their lives. We've heard a bit about magnetic fields and how that can affect their planets, and we've heard about the search for the study of this objects in our own solar system, like the icy moons of Jupiter. But now we're going to go a bit further afield and start talking about planets around other stars and what they're like. So this here is a picture of our galaxy, the Milky Way. And so we're inside our galaxy, so we can't really take a picture of the whole thing. So you may have seen pictures of spiral galaxies before that are really beautiful. But in the same way that you can't really put your arm outside of your house and take a picture of your house if you're inside your house, you can't really take a picture of your galaxy when you're inside it. And so the Milky Way appears to us as a white strip of bright stars across the sky, because our Milky Way galaxy is flat, sort of like a pancake, and we're looking through it. So the Milky Way has some 300 billion stars, and so a billion has 9 zeros. So imagine the number 300 with an extra 9 zeros, and that's a lot of stars. And we think that at least every one of these stars probably has a planet on average. And our solar system, for instance, if we think about it, we have 8 planets. So there's a lot of planets out there to be discovered. And we've only found around 5,000 of them so far. So that may seem like a relatively small number, but think back a few decades, about 30 years ago, we were only discovering the very first planets. And so that we've got that number up to 5,000 today is pretty incredible. And it continues every few days, we're discovering new planets. It's really the golden age of, exoplanets and discovering planets around other stars. But let's take a step back. That's like the big picture. How are stars and how are planets made? So stars form from the interaction of gravity with massive clouds of gas and dust in space. And so this here is a picture taken by the Hubble Space Telescope of the Eagle Nebula. And we can see it here in visible light. And so what it looks like is a massive, massive fingers, massive columns of gas and dust in space. And you can see some stars in the background, but you can't really see too many stars in the nebula itself, this big cloud of gas and dust. But if we switch to infrared light, which is light that's too red for our eyes to see, but is the light that, say, security cameras or night vision goggles use, we can begin to see through the cloud. So I'll flick back and forth, and you can suddenly start to see stars that you couldn't see before. And so we need all sorts of light to study the universe. And so these are what we call stellar nurseries. They're where baby stars are being born, because gravity wants to take that big cloud of gas and dust and collapse it and smush it down and make a star. But how does that happen? We can't go back in time and look at how the sun was born, and stars take millions of years to form anyway. So how are we going to watch the complete process? Well, one way we can do that is by using a computer simulation. So we can program the laws of physics into a computer. For anyone who's ever, say, played a video game, video games have laws of physics in them too. Like you can jump in a game and the gravity pulls you straight back down. And so in a supercomputer, which might be the size of this very building that we're in, you can program complicated laws of physics, such as gravity or how light behaves, and use it to simulate a star being born. So what we're going to see here is a computer simulation of baby stars being made with gravity. And so on the left, we're zoomed out, and on the right, we've zoomed in, and you can see the cloud, the gravity pulling stuff in a spiral and spinning it down and making these flat pancakes called disks, which are where the baby stars are going to be born. And this process is happening inside the Eagle Nebula and inside other nebulae that are all in the sky of the Milky Way and other galaxies. And so Astronomy is a really good field for both looking at the universe but also studying things in computers because stuff takes a really long time to happen in reality. But all right, we've simulated this in a computer. Is real life like this? And the answer is yes. So this here is a picture of a baby star. So, and I say baby star, but what I mean is the disk around a baby star. And this disk is making planets. So this is around the star HL Tau. And all the gaps that you can see here. So this disk here is much bigger than the solar system. And the star is in the very middle of it, and the light that we're using to look at this disk here is in radio waves. And so what we can see is the gas glowing. And there's a lot of gaps. And those gaps, we might wonder, are those caused by planets? Are baby planets orbiting this star and gobbling up all the gas and dust as they go around their star? Or are the planets kind of pushing the gas and dust away? But nonetheless, the fact remains that we can take pictures of these stunning objects in the night sky, which the sun might well have looked like 5 billion years ago. And it's not the only one. Here are a bunch of others. And they're all kind of unique. Some of them have thick rings, and some of them have thin rings, and some of them have spirals, and some of them aren't even just one star. Some of them are actually multiple stars together. And these are where baby stars are born, and baby stars make baby planets. But how does the solar system compare? So that's how the solar system was born, but let's think about the planets themselves. So we get a pretty picture when we think about the solar system. This is to scale in terms of the size of the planets. So Jupiter is really this big compared to Saturn, and Earth is really that small compared to Neptune. But Jupiter isn't that close to Saturn, for instance. But what we can see is we've got the sun on one side, we've got our 4 rocky planets in Mercury, Venus, Earth, and Mars. We've got 2 gas giants, we've got 2 ice giants, and we have an asteroid belt between Mars and Jupiter, which is sort of like the garbage heap of the solar system. A bunch of rocks left over from when we made the planets. And then out beyond Neptune, we have something called the Kuiper belt, which is sort of like an icy asteroid belt, and that's where Pluto lives. And so I'll just point out this thing down the bottom of the screen. That's actually the scale of the solar system. And so you can see all our rocky planets are really, really clustered close together. And then the gas planets are really clustered far apart, and Pluto's really, really, really far away. The solar system is really big. And if, you're asked to think about how close the planets are together, always guess a bigger distance. They're not close at all. But if we think about what kind of planets we have, Mercury is a rock. It essentially doesn't have any atmosphere. There's a small trace amounts of gas on Mercury, but otherwise it's mostly just a rock like the moon floating through space. The Earth, as we're quite familiar with, has an atmosphere, but it's very thin. Think of like the skin of an apple. Like the skin of an apple exists, but compared to how big the apple itself is, the skin actually isn't that large. Then we have something like Neptune, which is what we call an ice giant, and it's got quite a lot of atmosphere, something like 20% of the mass of the stuff that's in Neptune is gas. And we say ice because, they're larger molecules, stuff like water or ammonia stuff might be in Neptune. Heavier gases. And then we have something big like Jupiter. And Jupiter is mostly gas, something upwards of 90% of Jupiter is made of hydrogen and helium, and hydrogen and helium are the most common stuff in the universe. But the label gas giant is a bit misleading because you might just think like a puffy cloud like in the sky, and airplanes fly through clouds all the time. But you can't actually fly a spacecraft through Jupiter or Neptune or any gas planet because they're actually, think of it more like a submarine you need a submarine to go to the bottom of the ocean so the ocean doesn't crush you. And it's the same way going into these. It gets very hot, it gets very dense inside them, which is why you can't just fly through them. But this is what we have in the solar system. And as I said, the layout of the solar system we touched on before. But what are other star systems like? So here's the inner solar system. We've got our 4 rocky planets, and we have Jupiter nearly at the edge of the screen. These distances are to scale here. Well, the very first system of planets around a star like the Sun that we found is around a star called 51 Pegasi. And Mercury in our solar system takes about 88 days to go around the sun. But 51 Peg, its Jupiter-like planet, goes around its star in a few days. Not 88 days, but a few days. And so it's a really small system compared to the solar system. Then we have the TRAPPIST-1 system, which has 7 planets like the Earth, which all go around inside of 20 days. And so it's a very, very compact system. And then we have another system called Kepler-47, and it has 3 planets that are sort of like Neptune, but you might notice there's not just one star there, there's actually 2. And so these 3 planets go around 2 stars. The 2 stars go around each other, and then the planets go around the 2 stars. And so most stars in the night sky are actually binary stars. And Kepler-47 is one of those systems. Now let's zoom out a bit. Here we've got the outer solar system. So we've got Jupiter, Saturn, our ice giants, and Pluto. And here's a system called HR 8799. It'd be cool if a lot of these systems had really catchy names, but the thing is, there's 300 billion stars, and in the end, a lot of them just end up with numbers rather than really unique names. But the interesting thing here is, this system is much bigger than the solar system, and it has Jupiter-like planets that are much further out. And I'll touch on this system a little bit later, but this system's quite a young system, and these Jupiters are really, really hot and really, really bright, which means that that's how we discovered them. And so touching on how we find these planets, like there's a lot of different ways that we can look for them, because some planets are close to their star, some are further away, some stars are close to us, some stars are further away. So what kind of techniques do we use, or what kind of tools do we use? So the first most logical answer is we use really, really big telescopes. So there's a collaboration of European nations called the European Southern Observatory, and they operate telescopes in Chile, in the deserts of the Atacama Desert, which is really high up in mountains, and the sky and the weather is really good for doing astronomy. And so those 4 big telescopes in this picture, they have mirrors 8 meters across. So you could really only fit those mirrors in this room if you stood them up. And there's 4 of those telescopes on this mountain, and there's another 4 telescopes on that mountain that have 1.8 meter mirrors, which is, a little bit shorter than I am. And so this is one of the biggest telescopes on the planet. On the other hand, we can use small telescopes. Big telescopes are really expensive to build, and then when you build them, lots of people want to use them. But say if you yourself or your research group got some small telescopes, you could have a lot more small telescopes than you could have big telescopes. So, for instance, this is the HAT-South project that looks for exoplanets. And what they do is they have telescopes in Australia, in Chile as well, and in Africa. And so as, the Earth turns and as it's day somewhere, it's night somewhere else, this means that these telescopes can always be looking at the same stars 24/7 because there's telescopes all over the world. And these telescopes are only about 20 centimeters across. They're pretty small. And then there's space telescopes. And so these telescopes are some of the names that you may recognize. There's Hubble, we have Spitzer, we have Corot, Kepler, TESS, Cheops, and recently JWST, which launched at the end of last year. And so there's a mixture of European and American satellites here. And the reason that we want to go to space is that there's no weather in space. Well, there is, you heard about it before, but there's no rain in space. And there's no clouds in the same way in space. And so, if you go outside today in Uppsala, it's kind of cloudy. And so it's a bit tricky to do astronomy, but there's, these telescopes can look at whatever they want, whenever they want. How do we use them? So probably the easiest way to find planets is the so-called transit method or the eclipse method. Here's a picture taken from the Earth of the planet Venus in our own solar system transiting or eclipsing across the surface of the sun. And so the graph that's to the right of this shows the light that we're getting from the sun over that time. And you can see it dips down and then comes back up. And so if we look at stars for a long enough period of time and consistently, for instance, like what HAT-South was doing, you can look for when your stars get a little bit dimmer. And then if that signal repeats, say it might repeat every month, it might repeat every week or every year, But if it repeats, you know there's probably a planet going around. But if it only happens once, it's probably not a planet. And so we've got telescopes on the ground that do this and telescopes in space. But one of the tricks here is that not all planets can you find this way. Because some planets, if you imagine my head as a star, some planets pass in front and block the light. But other planets will, go around like this and not block the light. So we can only find some planets this way. Another method is the so-called Wobble Method. And the gravity of a planet is much smaller than the gravity of a star, but it still has gravity. And so what happens if I, if I was, dancing with someone and I held their hands and spun around, we would spin around a point that's in the middle of us. But if I spin around with like a kid, a child, we're more spinning around me, but I'm still doing a little bit of a spin. And so that's what this picture is showing, this video here is showing. There's a planet orbiting a star, and they're actually orbiting their common center of mass. So the star is doing a little bit of a wobble. And what that looks like is if we look at its rainbow, the rainbow kind of shifts towards the red and then shifts towards the blue as the planet as the star is moving towards us and away from us. And with a sensitive enough camera and a sensitive enough what we call spectrograph that can split the light into a rainbow, we can find planets this way. Another kind of tricky thing to use, so this is a little bit of step up in difficulty, is what we call the transit timing method. So the gravity of planets not only affects their star, but it also affects other planets. So here we have a planet that's just the only planet orbiting its star, and you can see every time it crosses in front of the star, it happens at exactly the same time, at the 12 o'clock mark on this clock. But then what would happen if there was another hidden planet in this system that wasn't crossing in front of the star, so we couldn't see it, but that secret planet has gravity. And so if you watch this picture, this blue planet is going to go around and it's going to be tugging on the other planet, the orange planet, and make it so that the orange planet is going to eclipse either a little bit later or a little bit earlier than we'd expect it to. And so the existence of systems of multiple planets means that we can sort of, use their gravitational influence to discover hidden planets. And so this is a bit of a trickier technique. So by far, probably one of the most difficult techniques to do, though, is to spot the light of planets directly. And so this is that system I mentioned earlier of the baby Jupiters. And so planets are really faint. So the analogy here is, if you're looking at a lighthouse, it's like trying to take a picture of a firefly that's flying right next to the lighthouse. Fireflies are not very bright compared to lighthouses, so you have more luck spotting the firefly if the firefly was further away from the lighthouse, or if it was a brighter firefly, or if you could find a way to kind of block the light of the lighthouse. And so this is the reason we use this technique for planets that are really far away. So these, as we saw before, this solar system is really big, and all these Jupiter planets are really far away from their stars. And they're also really young, and so these planets have just been made. And in the same way, when you pull a freshly baked loaf of bread out of the oven, it's quite hot. These planets are quite hot, and so if we look in infrared light, they're really bright. But this is really tricky to do, and we haven't found that many planets this way, but it's pretty much the best way to find planets that are far away from their stars. But that's pretty much everything I wanted to touch on. Like, when we want to find planets, we've got to think about how stars are born and how planets are born, but also the best way to find individual planets. If they're far away from their stars, we can look for them directly. But if they're close to their stars, we've, kind of got to study the star itself to find the planet. But there's a lot of different kinds of planet in the solar system, but also in the galaxy. And to understand them, we have to look at them, because the solar system is just one star system. But what we're finding is that every star system is kind of unique. And so to understand planets as a whole, we need to look at, the thousands of planets we've already found around other stars and keep finding more. But thank you for listening, everyone, and I'm happy to take questions.
All right, very interesting Do we have any questions from the audience? If not, then I have a question. So you mentioned that you could find planets, all these different methods with which you could find exoplanets. Is there any way to detect if these planets have moons?
Ah, yes. So if we pop back to this slide, so we haven't found any moons yet, but if you could imagine if Venus had a moon, Venus and its moon would be spinning around. And so zoomed in like this, you would be able to maybe see a second shadow if Venus and its moon were separate. But then it becomes tricky because what if Venus and its moon were crossing the sun when they were lined up? And so the trick then is, as with everything with planets, you've got to observe it carefully and a lot. Like you can't claim that you found a planet that's transiting its star if it just crosses the star once. You ideally want it to cross 2, 3, ideally as many as possible times. But there have been a couple of cases I've seen that astronomers have maybe gotten a bit excited that there might be a moon. There's nothing definite yet, but we'll absolutely find one because, for instance, Jupiter has really big moons, and there's bound to be other systems out there like that. But we'll have to be really analyzing, studying this data, and being able to definitely say it's got a moon or a ring system will be very tricky, but it's guaranteed to happen and they're guaranteed to exist, but it'll be tricky to analyze the data.
All right. Any more questions? I'll come with the microphone.
Yeah, there are groups of stars moving around each other. Is there any known planet in such a system of stars, or will they be disturbed and destroyed by gravity when the stars are moving around?
Good question. So that system I mentioned before, there's actually two, it's what we call a circumbinary system. And so there's two stars that orbit each other, and then the planets orbit them. But you're right about the planets getting destroyed because, for instance, it's like the TRAPPIST system that I mentioned, where it has 7 planets that all go around each other very quickly. If that was nearby another star, those planets would probably get destroyed because they're much too close to the other star. But I don't know if we found planets that go around 3 stars, but we've certainly found systems that are what we call like hierarchical. So you might have 2 stars that go around each other, and maybe there's a planet going around them, and then there's another star going around the 2 stars, and maybe that star has planets. So there are certainly some very complicated systems, but the more complexity means that it's harder for planets to exist. So in our solar system, we don't, the only thing affecting where the planets can be is kind of the other planets. But like if there were no other planets, you could just pop a planet down anywhere and it would happily go around the sun. But if you've got 2 stars, then the places where you can have a planet be happy is much, much less. And so, for instance, there are researchers who do study this, and they do have computer simulations running on supercomputers to figure out how planets are born differently around binary stars or triple stars or even more versus stars that are just like single, like the sun, because most stars in the sky are in binary systems. So we can't just study planets around single stars.
Do we have any more questions? I can ask one more. Is there any lower limit to, or I assume there is a lower limit, but what is the smallest planet that has been detected by these methods?
So I think the smallest planets that we've detected are around the size of Mercury. So the trick is that, in principle, with the transit technique, you just need to collect a lot of light. So the bigger your telescope is, so collecting light is like collecting rain. If you want to collect rain, you could put a bucket out, and that's like a small telescope. Or you could put a swimming pool out, that's like a big telescope. Or you could have lots of buckets together. And so a lot of the planets that are easiest to find are the biggest ones, and we can do that with small telescopes. But to find the really small ones, you're going to need to either look at the star a lot and kind of add everything up together over many years, or you're going to need bigger telescopes. And so, yeah, I think we've only discovered about the size of Mercury, but as we get bigger and bigger telescopes and as we get more and more data over the years, we'll certainly be able to like start finding more planets that are smaller. But we're kind of limited with the techniques and the tools that we use. And as we heard some of our previous speakers, stars are also complicated. And stars have activity and magnetic fields, and they flare, and they get brighter and dimmer, and that's dangerous for planets. And it also means that when you're looking at a signal like this, a sunspot that was so those other black dots on the sun, those are sunspots. And you could maybe get confused as to whether a sunspot that's on that picture, on that video up there, which also goes around the sun, that could look very similar to a planet in your data. And so you've got to be very careful when analyzing things to make sure it's actually a planet or whether it's something about the star.
Well then, do we have any more questions? Otherwise, I would like to say thank you. And this wraps up the streams for today and the talks for today, right? Will we see any more of this?
Hopefully, this was good fun, and I hope everyone who attended enjoyed and maybe learned something.
And does this, is there anywhere else where you could go to see anything more astronomical today?
Yes, so across the street, if you're in Uppsala, there's the old observatory, which hopefully is still open. But in general, like there's a lot of good places if you're just online, like NASA or the European Space Agency or the European Southern Observatory. They always have a lot of resources, and there's always a lot of astronomers talking online because we love talking about our science, and astronomy is really exciting. So there's a lot of good places to find interesting space stuff.
Well, I will definitely check those places out. I hope you guys do too. So thank you very much, and we will see you next year.